What have we covered so far on this subject that we started about a couple weeks ago? First thing is that mathematics does not have distance. They have no idea what distance is. They don't use the distance of physics, which is separation. Okay? No, they use the distance traveled. They unroll the end of their measuring tape every time they talk about distance. So because a mathematician cannot put in an equation separation. That's a qualitative concept. They have no place to put it in an equation. Makes no sense. Now they have to put a number. And what number are they going to put? Followed by a unit. They got to put meters per second. What is meters per second a distance? No, it's a distance traveled. Or they put meters. And you say, well, what do you mean meters? Well, it's the amount of meters that the end of the tape unrolled to, which is, again, meters traveled. Maybe it's not meters per second, but it is the quantity of meters. Okay? And so distance traveled is not equal to distance. Distance is what we have in physics, separation. That's qualitative, has nothing to do with the notion of math, which is distance traveled, which again is how many meters. How many meters did you unroll the tip of your measuring tape? Okay? And so, yeah, distance in math is total amount an object has traveled in a period of time. Okay? And synonym is length. See, they measure length in the same way. In other words, you want to know how long the table is? What you do, you unroll, first you create a standard, the meter, for example, or the foot, whatever. And then you unroll the measuring tape. And you say, okay, I got 5 meters from here, from the beginning of the table to the end of the table. So are you talking about some kind of separation? Are you talking about distance? No, you're talking about distance traveled in every case, whether you measure length or distance or even position, as I've got there. Distance traveled is equal to position and equal to displacement equal to length. These are synonyms. There's no difference between them whatsoever. Okay, and people say, well, what are you saying, Bill? Yeah, I'm saying that exactly. Let me show you why. Here's position. Okay, you say position is a static concept, right? Here I am. I'm at this position, right? No, not in math. Okay, they can't use the word position for anything. So what they did, they turned it into a dynamic concept. Okay, here it is. Okay, this is position. You got the treasure map. You got the treasure over there, upper right-hand corner. Okay, and what you're staring at is not position of the treasure chest. What you're staring at is the spec, the recipe, the way to get to the treasure chest. You're talking about instructions on how to get there. And what you have to do is you walk 34 paces to the right and 15 to the north, and you arrive at your treasure chest. That's the position that they use in mathematics. So they're talking about 2 itineraries, okay? And or you can go like the ship there, you know, you can dock and then from there walk all the way to the treasure chest. Each one of those red dots, that's a position. What is a position? How to get there. So there is no such thing as position, the qualitative concept in mathematics. They have no use for that. What they have is motion. Mathematics, I call it, right? All they do is have motion. Mathematics only has use for motion, has no use for any static concept. So yeah, all those are synonyms because they all involve motion. There are little things that concern mathematicians. They say, well, this distance is different than position, which is different than displacement. Petty stuff that only concerns mathematics. It has no bearing whatsoever on physics. Okay, and so all these are dynamic concepts in mathematics because otherwise they couldn't use it in any equation. Okay, and velocity, well, again, we have here the situation where velocity, a single value in space and in time. That's what velocity is. Okay, what is velocity? A motion in one frame of the film. So how can you have motion in a single frame of the film? It's like if you take a cross section of time and that's velocity at that cross section of time, which has no width whatsoever because you're talking again about concepts. You can't chop concepts, but that's essentially what they do. They have the timeline, the number line in seconds, minutes, hours, whatever they want. They cut through it. They slice through it as thin as you want using God's sword, right? And once you get to that point, you say, well, that's the velocity here. But see, if you had no direction, all you would have is speed. The way you turn it into velocity is by putting smiley there. You have to show that that single point has direction. So you have to put a face on smiley because we have to know which way he's pointing with his face. Okay, so velocity is that combination of speed plus direction. But direction is a qualitative concept, and they had no use in mathematics for qualitative concept. They can't put it in an equation. They can't do anything with it. Okay, so that's the recap. And one fellow out there says, I'm lost on this video. What exactly is Bill arguing for or against? I need velocity. I used velocity in high school physics when there was a ball on a slope with a gravity pulling it down. Yeah, gravity pulls it down, right? Whatever gravity is. Gravity is a physical object that pulls. Think about your wording, because people use that wording, and then when you say, well, if it's pulling, what's pulling on? You say, well, that's just a figure of speech. No, don't use it if you're going to say pull. Why didn't you say push? Why don't you say gravity is push gravity, like some people out there say, right? And if it's pushing, what does that pushing thing look like? Okay, but that's on the margin here. I wasn't being taught velocity in high school math, okay? You have a direction if there's gravity or the object has eyes. Yeah, for a single point, you have to have eyes. You have to show the crowd what direction that ball is moving towards. But let's go here in a little more detail, okay? Here's a velocity of the object. Okay, why does it have velocity? Well, because it's got a smiley face on it. Okay, well, he's not smiling very much, but imagine that. Okay, so you can see that he's going towards the what is it in your case, to the right. Okay, he's moving to the right. Why is he moving to the right? Well, because his face is pointed to the right. Okay, so that's the direction in which that ball is moving. And if you have the value of the magnitude of the speed, right, plus the direction, well, now you have velocity. Okay, but you have a single point, a cross section of time. Don't lose track of that, because velocity is a cross-section of time. It's just a single point in time. Gazillions of decimal points in time. Okay, so it's second number 5 with gazillions of decimal points. Okay, so that's what velocity is. And so you have to have a smiley face for direction, because if you remove the smiley face, okay, let's remove the smiley face, okay, now that object becomes more plain to see. Okay, here is dot the object, okay. Now you remove the direction. You don't know what direction that dot is pointing. Now all you have, if anything, is speed. Okay, and again, like I pointed out the other day, is unless you have a second point inside that frame of the movie, okay, unless you have a second point, you don't know in which direction that's going first, but you don't know the speed either, because you need a reference to calculate speed, especially, average speed. Okay, so this is where the problem starts. What you've done is essentially, without a reference, you have no direction, no speed. All you have is the object. You have the little ball that is at a point in time and point in space. That's all you have in front of you, objectively. Okay? And if you remove that, you have absolutely nothing. You have space. So you have to put something in there if you're going to talk about something. And then you have a something. What you have is a dot. That's the object called dot. Does that dot have speed and direction? No. Absolutely not. And this is the problem. What they've done is, by taking the limit, right, as x equals 0, right, what they've done is convert a concept called speed into a dot, into an object, into a thing. That's what they've done. The mathematicians don't care about object. They just care about their calculations. So they were at home with that. They said, no problem. We just calculate that value. Yeah, but what you've done from a physical point of view is by going, taking the limit of whatever limit you take out there, what you've done is zero in on an object, on the object itself. And the object here is supposedly location, but what is location without an object? Absolutely nothing. So you need the object to establish the location, which in this case is actually position, because for location you also need distance. Okay? So that in a nutshell is summary there, and here we have it, okay? Velocity, what is it? Well, first of all, speed is equal to meters per second. In other words, that's what you measure it in. Those are the units. You can have other units as well, but meters per second is the official version there. Velocity is the same thing, meters per second, because that's what they're going to put in the equation. Are they going to put direction in the equation? No, they can't put, so they never talk about velocity, essentially. They talk about speed. They talk about the speed of light, and they put, 300,000 kilometers per second. Is there anything there that gives you an idea of direction when you say 300,000 kilometers per second? Where's the direction? They can't put direction, so they never talk about the velocity of light. They talk about the speed of light, because again, they don't need to find out what the speed is at a given point, a cross section of time. They don't need the speed of light at that point. They just said the speed of light in general, 300,000 kilometers per second. They put the little c in there, right, which represents that value. And math has no use for qualitative concepts. You can place a qualitative concept. You can't place a qualitative concept in an equation or perform mathematical operations on qualitative concepts, such as direction. So direction is something that the mathematicians incorporated together with speed to create this concept known as velocity. They needed it for angular momentum. Okay, when a planet moves around, they said, well, if it's in a straight line, no problem in speed. No problem. We don't have any problem there. But when it turns the corner, now what do we call it? Well, they had to invent this notion of speed, and the only difference between speed and velocity was the direction. Okay, because as long as they're on the same line, displacement, speed, position, it's all the same. Okay, And so, they can use all these dynamic concepts, just assign different names to them because they have minor differences between them that don't concern physics at all. Okay, and they can't put the qualitative notion of each one of these in an equation. All they can do is put the value that they need for whatever calculation they have to do. Okay, again, what is velocity? A single frame in the universal movie. Make that frame as thin as you want, as small as you want, because it's a single frame in God's movie. Okay, so can you have direction in a single frame? Can you have even speed in a single frame? No, you can't. But mathematicians manage to do it through, again, taking derivatives and so on. Okay, give me a second here. Here we have, continuing with this, here we have the conclusion, I guess, of this. What are the differences between math and physics? Well, in math, you have distance traveled and displacement. They could be the same if it's on a straight line only. But if distance traveled is curved, then we have different values and different notions. They say, well, this one's displacement and that one's distance traveled. The distance you traveled from S1 to S2 is on a curve. Okay, so that's a value that's different from displacement, which is just a difference in locations of these two points. And so, in physics, we call it something different. We say the top one, the blue one, is called motion. And we usually represent it with dashed or dotted lines to show that it's segmented, that it's a bunch of locations. And, you can fit as many locations as you want in there. The object only can have one location, so it's a discrete location no matter what. When it moves to another location, it's discrete again because the previous location disappeared, right? Now we have that concept that continuously disappears in the back and recreates itself in the front. So we use a dotted line to represent motion. And we don't call it distance traveled, we call it motion. That's all it is, okay? And displacement, if it's just a separation between S1 and S2, we call it distance. All we're talking about is the separation between those 2 points. And so you can see that one is qualitative, the other one is used for calculations. And so I like to summarize that and say distance is what is between lengths. Why? Because distance is not the same thing as length in physics. They're 2 different concepts altogether. Length is what is within an object from one face to the other. That's what we call length. That's separation. And distance is what is between 2 objects. And that's not the case in mathematics. For them, it's all the same thing. Distance, travel, displacement, length. It's all the same because all they're doing is stretching the measuring tape from one end to the other. They don't care what they measure. What they're actually measuring is the measuring tape itself. When the astronaut goes to space, right, and he stretches his measuring tape across space, what he's measuring is this measuring tape, not space. Okay? And that's the issue. But in math, you can get away with that because you don't deal with objects. You're dealing with abstractions. Okay, and so here, let's move on to time. And how do we come to the subject of time? Well, we come to the subject of time because, remember, speed is equal to this distance divided by time. And now what we're going to do is put time on the other side and speed on this side, right? We're going to change them there. And we're going to find out what the definition or the notion of time is. And there's a difference again here between mathematics and science, between mathematical physics and physics proper, genuine physics. Okay, so let's start here. We start where? At Aristotle, because see, Aristotle, he was one of the first guys. In fact, I think it's the first precedent that we have. I don't know about the East. Maybe some Chinese guy did the same thing. I have no idea, or an Arab or whatever. But as far as I'm concerned, Aristotle was the first one to analyze time in quite a bit of detail. Okay, and so I'm not going to give you his whole notion. Let me get it here. I'm just going to show you here how he went about thinking about time. Okay, and what we inherited from him. And so he started his reasoning here. He says, Physics Book 4, okay, he says, time, does it belong to the class of things that exist or to that of things that do not exist? So he wanted to know, or he wanted to get to the bottom of whether time exists or not. That was one of the issues. And then the other issue, he says, what is its nature? I mean, what is time? Okay, so he wanted to understand that. Okay, that's where we start. And let's see where he went with this. Well, he did this analysis. Essentially, I just took bits and pieces to give you the main points, okay? So you don't have to read them all over again, but you can. It's in book 4 again. And he says, time is present equally everywhere and with all things, okay? So he said, everything is affected by time. Time is continuous, by which he meant not that it's what we call continuous, made of a single piece. No, for him, continuous means it's divisible. That's what it means. Exactly the opposite. That's what continuous meant to I guess not only Aristotle, but to the Greeks in general. Time is neither fast nor slow, but many or few, long or short. Okay? Time does not exist without change or movement. But if we have change or movement, I guess then you can say time exists according to Aristotle. Okay? So we have something here that's saying time does exist. The only condition is that it have change or movement. Time is a measure of motion. Okay? Some kind of measure of motion. Time is not movement itself, but movement insofar as it admits of enumeration. Time is what is counted. Okay? So time refers to the number that you use to describe or count movement or change. Time is number of movement in respect to of the before and after. Okay, so these are the starting points of humanity, I guess you could say, our notion of time. It had to do with Mr. Aristotle doing an analysis, and he's saying essentially that number is not time, but what you enumerate is time. What are you enumerating? Amount of motion. Okay? So he said, what is time? Essentially, it's motion. It's numbers applied to motion. Okay, that was his overall notion. We're going to short circuit all the guys in between because they didn't add really very much to the word time until we get to the 17th century. Okay, 17th century, you can call it the century of time for several reasons. First, well, we had the scientific revolution. That's what the 17th century is typically known for. Okay, invention of the calculus. We had these two gentlemen, Mr. Leibniz and Newton. They're fighting over who invented the calculus, but they both apparently developed it, invented it. We use Leibniz notation today. We do not use Newton's at all. Okay, and also what discovered in those days, or what was invented, what was proposed, is the wave nature of light by Mr. Hooke. Okay, he was the first one to talk about the wave nature. It was later developed by Huygens, okay, Dutch fellow. And both Huygens and Hooke, they also worked with clocks. This was a time where people were talking about clocks and time started becoming a more important issue among the theorists. And one of the first ones was Galileo Galilei. And what Galileo did was he tried to measure the speed of light. And very awkward. I showed that in the past where he had his assistant in one mountain, he was in another mountain, and they had their lanterns covered. And they said, look, when I uncover my lantern, I want you to uncover it immediately as you see the light. Uncover yours so that I can see your light. And they kept doing this, like uncover, and the other guy uncovered, and they said, light is faster than we can uncover. And so he concluded that light was instantaneous. There was no speed to light. And that would change with Mr. Romer, a Danish guy who eventually showed that because of one of the moons of Jupiter, the light coming from when the moon was behind Jupiter and when it was in front of Jupiter, as it rolled around, they said, well, what's the difference? That moon should have come out earlier. And the reason it came out later, he said, is the speed of light. It takes light time to get from that moon to our eyes when it's, on the other side of Jupiter. And especially, when there was a difference in like 6 months difference where Jupiter was on the other side of the Earth, the Earth that was now here, it was close to Jupiter, here it was farther away. And now why was there a difference? Well, the speed of light. Okay, and that's what Romer discovered. So, they were looking at the relationship between time and the speed of light. And, a couple decades later, you have, James Bradley. He also used parallax to determine the speed of light, calculated value always. And until you get to the 19th century, people like Foucault and Fizeau, they started measuring light. Again, always round trip, okay, in their case. And what they did in most of these cases is calculate angles. Okay, so this is essentially where we are today. We don't have a one-way speed of light. As far as I know, there's been no experiment on one-way speed of light. They should do one because I think we have the capability. And the way we would do it is by sending someone to the moon. And it takes light 1 second, and not quite 2 seconds. It's a little over a light second for light to reach from a laser here on Earth all the way to the moon. And so we would have a one-way mechanism that someone, maybe an astronaut, could measure somehow by receiving light one way. Okay, and so, but again, the problem there would be communication. It's more or less like Galileo's lantern. The guy here says, "Okay, I sent the laser." The other guy said, "Okay, I received it." The sound would also take speed of light to get to the moon. So I don't know. Maybe there is a way of doing it. Someone smarter than me can figure it out, but I don't think it's important at all. Light in physics, we say light is fast. Is that accurate enough? Okay, it's very fast. That's a little more accurate. That's all we need. Light is fast. Now we got to figure out what light is. And likewise, we have to figure out what time is. Is time something physical? Is time something related to to physics at all? Do we need time in physics? Or is it just a calculation that they need in mathematics, which is unrelated to physics entirely? Okay, so this is the question. Okay, so here we get to Mr. Newton, and he more or less synthesizes the notion that people had in the 17th century about time. What is time? And here Newton's going to give us the scientific super duper definition of time. Okay, here it is. It says, I do not define time, space, place, and motion as being well known to all. Yeah, all these people work with force, which involves time, acceleration, which involves time, speed, velocity involves time, all that involves time. No one knew, no one could define the word time because, as he says, well, we all know what time is. And just in case they didn't define motion or space, because we all know what that is as well, so we don't have to define any of those things. You just go with your intuition and say, okay, I know what motion is, I know what space is, I know what time is. And then you have today, 21st century, and the mathematicians are saying space is made of particles. So it's a little different than what Newton probably thought of space, and means that no, Newton, you did not know what space is. No one knew what space is, because now they're saying space is a physical object. It's a block of stone made of particles that come in from the void and separate into positive and negative. So do we know what space is? Well, we don't know what space is. I guess we don't know what time is either. So what do we know? I mean, the mathematicians, right? And do we need this at all? Do we need time at all? What is time? Do we need it? Do we use it in physics? In math, obviously, they use something called time. Do we need it in physics? Okay, so let's continue. Let's find out what this time thingy is. Here we, again, short circuit to the 20th century, and we have Mr. Einstein, and he started bending time. He treated time like a physical object. And so now it gets very scary, because Newton probably would disagree that time is a physical object. He said, look, we all know what it is. It's what we measure with a clock, essentially, right? But here we're talking about something else. Here this guy is saying, we're going to bend time. What do you mean bend time? You bend it like a hammock or what? What do you mean you're going to bend time? And you can say, well, Bill, that's a figure of speech. It means something else in mathematics. Well, yeah, we got a couple problems there alone. And the first one is that 90% of the people out there, they just repeat what the mathematicians tell them. And they say, oh, Einstein proved that time could be warped. And they don't even know what they're saying. Because what they did is they took the closing argument, the figure of speech, and that's what they spread out there. And they say, well, Einstein proved, and every mathematician believes that time is warped. That's what they tell you out there. Now, the mathematicians who know better, they say, well, we don't really warp time. This is the explanation. They go through this rigmarole where they say, okay, I'm going to explain to you what we mean by warping of time. See, but that's not what they use, because you can't use the word warp with time, because otherwise you're treating time as a physical object. So you have to go in there and explain to them really what you mean by time warp or whatever. But see, that's one issue. The other issue is they're trying to give a physical interpretation, and they're using this thingy called time, which is not a thingy. And so you can't give a physical interpretation of causes and mechanisms using the word time, which is what the mathematicians pretend to do or purport to do. So they're telling you, look, we can tell you how this universe works. Okay, how does it work? Well, see, you have this thing called time. No, it's not a thing. And we warp it, but you don't warp it. Well, what we really mean by that is, and you say you can't do that because all you're doing is a description, a mathematical description, which you're somehow converting in your language into a physical object, and then concluding, your closing arguments to the jury, you say, well, we warp time. So you took a big leap into physics. As long as you keep it in mathematics and say, look, it's just a calculation, no problem. It's when you bring it into what you call mathematical physics, with quotation, that's where we run into trouble, because now you turn it into a physical object. You insinuate to the masses out there who don't know any better that you actually warp time, and when people start questioning you, you say, well, you took it too literally. Well, what was your intention of giving me a physical interpretation using the word time? What was the purpose? Okay, so we have a problem there, a serious problem, because if the mathematicians cannot give you a physical interpretation, they should stay out of it completely. They should stick with their math, their equations, their calculations, and not pretend to understand how the universe works, meaning causes and mechanisms, not descriptions. If you can explain how the universe works physically, come in there, but don't bring time with you. Leave time in your own field, in your own discipline. Okay, here we have Quora guy, and he says, talking about Einstein, he says, Einstein realized that a watch doesn't measure time. Okay, thank God for Einstein. Instead, it measures motion, which is what Aristotle said. And this guy got thousands of views and thousands of thumbs up. And it turns out he's saying something he doesn't even understand. Obviously, this guy never read Aristotle, because Aristotle already said, what does time measure? It measures motion. And this guy gives credit to Einstein 2,000 years later. Yeah. Motion is, of course, the combination of time and distance. Okay, how do you combine numbers with distance, meaning separation, if that's what you're talking about? Maybe it's not distance, maybe he meant distance traveled. Okay, and measure time without motion, it's impossible. Yeah, no kidding. You need motion to talk about time. But what is the relationship between motion and time? That's what all these people failed to identify, to discover. And you'll read out there, time is what you measure with a clock. That's one of the definitions out there they put out. And you can look up and say a clock is what you measure with with time. So what you use to measure time. So the question is, you got a circular argument there. We don't have a definition for a clock or for time. What is a clock? Well, it's what you use to measure time. What is time? Well, what is measured by a clock? Great. We learned a lot. Yeah, these are the definitions you'll find out there, and they're no good. So we need a definition if we're going to use the word time, and we need to determine, once we define that word, whether it belongs to physics at all, whether we have any use for it in physics. Okay, so here we have scientific definition of time. What were all these people talking about all these years? Okay, here it is. Again, we have that math, which is distance traveled. Okay, and if it's in a straight line, it's the same thing as displacement. But if it's curved like there, then there's a difference between distance traveled and displacement. So what do mathematicians do? Well, they go in there and they say, look, speed is equal to distance divided by time. Okay, what they really meant is speed is equal to distance traveled divided by time. Two dynamic concepts there, okay? And then when we go to time, we can just do the little, calculation there, or put things on different sides of the equal sign. We have distance traveled divided by speed. That's what time is officially from math. But what did we say that distance traveled is? Well, it's motion. And what is displacement? Well, it's distance separation between two objects. Here we're talking about two motions. We're saying that distance traveled divided by speed is two motions. And so time is equal to motion divided by another type of motion. In other words, you need two motions to talk about time, okay? And of course, what's missing in all these cases is memory. You absolutely need memory to talk about time. Okay, so here we have the definition, scientific definition. What is time? Take it from me there. Qualitative time, qualitative relation established between two locations of an object or between the trajectories of two objects. What are we measuring? We're measuring the motion of a clock, for example, the hands on a clock, against the motion of the earth around the sun. That's what we're comparing. We're comparing two motions every time we use the word time, whether we know it or not. And what you need here is memory, because in order to be able to do this, you need to remember the motions. You need to remember the starting points and the ending points. You need to register them somewhere. So that's what time is. Time is simply a comparison of two motions, and you need memory for that. Okay, and quantitative time, which is what they use in mathematics, which is a value, okay, is a numerical or quantitative relation established between two motions, one of which is a pre-established standard. And again, in both cases, you need memory. You can't do time without memory. Okay, memory is a key aspect of time. So we need memory and we need two motions. So time is not the same thing as motion, because time is a comparison of two motions. You need two motions in order to have time. If you have a single object moving in the universe, you still don't have time, because you have no reference for that object except its starting point. All you have is motion. You need two motions and memory. Okay. And so let's go with the conclusions here so that you can take something home with you. Okay. And these are conclusions. No one has ever defined the word time scientifically. Okay. Time is not equal to an object, which is what they say it is, because they're going to bend it, they're going to warp it, they're going to use it in that sense. And 90% of the people out there believe that it's some kind of object, because they say, well, we warp time. It sounds like, you're warping like warping a banana or something, So you're treating it as a physical object by default. And you can't warp or bend time, right? Because if you could, then you are actually talking about an object. And the mathematicians know better, but 90% of the people out there who, dabble in physics lightly, they are not very keen on this issue. They don't realize that they sold them some snake oil. They're telling them, look, we warp time. And the guy says, okay, the mathematicians proved that the experts the scientists. It turns out they sold them a fib. Okay? No, at least don't use that unless you understand what warping time means. Don't use that figure of speech unless you really understand it. And then from the speed equation, we can deduce that time is equal to distance traveled divided by speed, which in physics would be motion divided by motion. Obviously, we're not talking about a physical object. And so time is a comparison of two motions. Okay? And time requires memory. You can't do time without memory.